Hey y'all, my name is Prashant Kumar, or PK, and I'm an MCAT tutor at Shemmassian Academic Consulting. Today, we're going to be doing a passage walkthrough in the MCAT Chem Phys section, specifically dealing with Gen Chem. You should be taking roughly 6.5 minutes on this passage, but today we're going to be going more in depth so you can see exactly what's going on in my head as I tackle this section. Make sure to like this video and subscribe to our channel, and comment down below exactly what types of videos you're looking forward to next. Let's get it. All right, great. So I've gone ahead and put the passage on the left and the questions we're going through on the right. So feel free to take a moment, pause the video, and come back to us when you're ready. I'll go ahead and zoom in on the passage so we can get a good read. So there's paragraphs 1, 2, the figure, paragraphs 3, 4, 5, and then a reaction, and then question 1, question 2, question 3, and question 4. All right. So with that, take a moment, pause the video, come back to us. If not, let's get right into talking strategy. For me, I like to maintain the same strategy regardless of whatever type of passage I'm going through. Why? It gives me something to come back to, whether the passage is super easy or super challenging. I'm grounded. I know exactly what I'm going to do when it comes test day. And so that boosts my confidence and that boosts my ability to tackle anything that might come up on test day. Confidence saves time, and that's really important as we tackle more and more challenging passages. And so what does that strategy look like for me? Well, I like to read the first paragraph, write a quick 3 to 5 word summary right next to it, go on to the next paragraph, do the same, and on and on and on. Why do I do this? So for me, that quick 3 to 5 word summary at the end of that quick read gives me a mental check-in. Do I understand what's going on or not? It takes less than a second to think about those 3 to 5 words. Very simple writing, nothing too crazy. But it's accountability. Make sure I understand exactly what's going on before going on to the next paragraph. And so then, if I need to reread, I can just reread that paragraph. I don't have to reread the entire passage, which is what often happens, right? We start reading, we get confused, it goes in one ear and out the other, right? And so when we do this, we sort of make sure that we understand exactly what's going on throughout the entire passage. And so with that, let's get right into that first paragraph. Most biochemical reactions depend on the pH value of the aqueous environment, and many are strongly favored to occur in an acidic environment. A non-invasive control of pH to tightly regulate such reactions with defined start and end points is a highly desirable feature in certain applications. All right, so the question I always ask myself in these types of situations is, what's happening, right? So what is happening? And so here it's saying reactions favored at diff pH, right? And so here it's just talking about what the applications of such a thing is, but big picture idea, right? What's happening? Feel free to abbreviate, feel free to use arrows, symbols, whatever. At the end of the day, you're the only one reading this, so it doesn't really matter if it's neat, messy, as long as it makes sense to you. Researchers report a novel optical approach to reversibly control a typical biochemical reaction by changing the pH and using an acid phosphatase as a model enzyme. The reversible photoacid G-acid functions as a proton donor, changing the pH rapidly and reversibly by using high-power UV LEDs as an illumination source in the experimental setup. The researchers found that the reaction can be tightly controlled by switching a light on and off, making the technology applicable to a wide range of other enzymatic reactions, thus enabling miniaturization and parallelization through non-invasive optical means. Figure 1 displays the structure of the G-acid. All right, so lots and lots of details. And I don't want you to get bogged down by the details, but that big picture, what's happening, that's what I want you to focus on. So here, they're using UV to modify G-acid function, right? And so that's the big picture idea. Like, we'll come back to the details as we need, but the idea is we're changing the pH of this reaction by adding UV light or getting rid of UV light, right? So it says UV light is changing the G-acids, changing the pH or whatever, right? But we don't really care about those details. And so next we have a figure. And my next tip is to not spend too much time on the figures, right? Just give it a quick glance. You're not going to need to look at it on that first read unless a question asks for it, right? So why waste time trying to figure out exactly what's happening when we don't need to. And so here we see it's a reaction. You can even read the little bio of the figure, the caption. Light-activated deprotonation of G acid. We'll come back to that if we need to. In order to use the photoacid in a wide range of biochemical applications, the researchers ensured that it met certain requirements, such as solubility in water, low toxicity, and excitability with commonly available inexpensive illumination sources, such as LEDs. LEDs have several advantages compared to more conventional illumination sources. They are more efficient, have a long lifetime, a compact size, and high reliability. All right, so what's the question happening here, right? Here it's saying LED use to photoacid, right? So they're trying to see if the photoacid will work with these LEDs. The LEDs, why are they good? Because they're cheap. They're not caring about the details, but that quick glance and on to the next paragraph. The researchers chose an acid phosphatase as a model enzyme to further study the system. The activity optimum of APs typically lies at an acidic pH of 4.5 to 5.5. APs non-specifically catalyze the hydrolysis of monoesters to produce inorganic phosphate under acidic conditions. In experiment A, researchers used the acid phosphatase from potato, EC 3.1.3.2, which is active between pH of 4 to 7, with an activity optimum at a pH of 5 to 5.3. At an alkaline pH, the activity of EC 3.1.3.2 is several orders of magnitude lower. All right, so the question is, what's happening? Here, they're modifying the sort of pH levels, right? That's what they're saying. We have like an experimental A, right? So I'll just write A. And so they have lower pH, right? And higher pH. And that means increase activity and decrease activity, right? And so it's very important to use like symbols to understand trends, right? Decreased pH, more acidic, more activity. Increased pH, less acidic, less activity, right? And so here, that's the big picture understanding. We don't need to focus on the details of how this is happening, more along the lines of the trends. And so with that, we're on to our final paragraph. To assay EC 3.1.3.2 activity, researchers used PNPP assay. The PNPP assay is a colorimetric assay in which the substrate PNPP is hydrolyzed by acid phosphatase into the product P-nitrophenol, PNP, plus PI, and purified HPLC grade water as shown by figure 2. All right, so what's happening? And so here they're saying EC 3.1.3.2. I'll even write that up here just so we know it's the same phosphatase that we're dealing with before. And so we're saying what? We're saying here's the mechanism of it. And they're using PNPP to measure, right? So now we have our big picture summary of what's going on, right? They're testing sort of the mechanism of modulating activity levels of enzymes. Big picture understanding, and we have like a step-by-step process of understanding why that is. And so with that, I'm not even going to spend more time on this. We're going straight into question number 1, right? Which of the following best describes the role of water in the deprotonation of the G acid? Is it A, acid, B, catalyst, C, base, or D, aprotic solvent? All right, so right away, we're looking at sort of a reaction, right? So we're looking at deprotonation of the G acid. And where do we look to for that? Well, that's right here. We even underlined it when we took a quick glance, right? We're looking at this, and we're looking at the role of water. And we see water right here, H2O. And so we're thinking, what is water doing in this situation? And so right away, when you look at this, you see a combination of sort of chemical nomenclature as well as sort of organic chemistry sort of structures. But I don't want to think about that. I just see a reaction where we start with H2O and we're going to H3O plus, and we see exactly like we're losing a hydrogen here when we go to the other side, okay? So those are the two things that are changing, H2O to H3O, and sort of this G acid losing its proton. And so in this case, we should be having alarm bells ringing, right? What type of reaction loses and gains protons? Acid-base, exactly. And so here, what is water doing? Well, it's gaining H plus, right? It's taking away an H plus. And so what type of sort of substance takes away H pluses from another molecule that it's interacting with? It's a base, right? A base takes H plus, and an acid gives an H plus, right? And so here we have water as C, our base, right? The role of water in this deprotonization is the G acid. Now, if I asked you what was the acid in this case, right? The acid is what's giving away the proton. So that OH group right here is the acidic proton. A catalyst will never be included in sort of a chemical reaction, so we can eliminate B as well. And D, an aprotic solvent. So this doesn't really relate to this since it's part of the reaction, but what is an aprotic solvent? An aprotic solvent is a solvent that doesn't have any hydrogen bonding with the reaction or with the substances inside the reaction. So D is not true because water is a protic solvent, not an aprotic, right? It has those hydrogen bonds. And so with that, we can eliminate A, B, and D, and we're stuck with C, and we are 1 for 1. Onward to question number 2. All right. The researchers measured the energy of a photon during an experimental trial to be 3.3 times 10 to the negative 12th joules. What is the frequency of the wave? Note Planck's constant is equal to 6.6 times 10 to the negative 34th. All right, so right away, this is a standalone question. We notice that they give us a value. They're asking us for another value. They don't really care about the passage at all. So this requires us to remember sort of an equation, right? So what do we have in this? We have the energy. We're looking for the frequency, and they give us Planck's constant. So right away, E equals H, Planck's constant, times frequency, right? That's the most direct equation we can think of right now that relates these three numbers. And so I always write the equation and then write underneath it, right? 3.3 times 10 to the negative 12th joules, right? Substitute directly in. And then we know Planck's constant is 6.6 times 10 to the negative 34 times V. Okay. And so now this is algebra, right? We're probably familiar with algebra. Not many of us love algebra. And so we're just going to have to deal with it, right? We're going to have to figure out little tricks and tips to help us do these fast, right? And so the nice thing about the MCAT is none of these calculations should require a calculator. They should be some sort of trend, trick, something to help you think that'll help you get to the answer immediately. All right, so let's go through this. So what would we do? We divide both sides by 6.6 times 10 to the negative 34th so that we have the V on its own. And I'm just going to go ahead and switch the sides just so we have it V equals. So we have V equals 3.3 times 10 to the negative 12th over 6.6 times 10 to the negative 34th. All right. And so now this is where you're like, PK, I'm stressed. I don't like math. But I'm going to tell you, these numbers are very, very clean. And I like to do it in two ways. I like to break it up into like the numbers part and sort of the magnitude part. And so here, the magnitude part is what I call the 10 to the negative whatever power. And this is like the number part. And so we're going to separate those two and try to break it up into easier things. And so here, the 3.3 over 6.6 is the numbers part, right? And so 3.3 and 6.6. What's kind of similar about that? Well, 3.3 is 1/2 of 6.6. So, right? That is just 1 over 2. And so what is 1 over 2 written as a decimal? 0.5, okay? And so right away, we see that the number should have 0.5 or it should start with a 5, one of those. And so we can, if we look at our answer choices, we can actually eliminate A, B, and C because none of them start with a 5 or a 0.5. D does. And so automatically, we're stuck with that as your answer choice. But let's just check our answer and make sure it's right. So now we have 10 to the negative 12th over 10 to the negative 34th. And if you remember exponential rules, right, what happens when you divide? Well, you subtract the bottom from the top. So minus negative 34. And so negative 12 minus negative 34 is negative 12 plus 34, which in the end is 22. So 10 to the 22nd is the power. And we see that exactly matching right here. So see, those are the little tricks I love to use, right? Why do all the math and waste a little more time when we can do half the math? Or do half the math and use the other half to check our answer? And so with that, we're 2 for 2. Crush that one. Onward. Question number 3. Which of the following functional groups is not found on the protonated G acid? Is it an alcohol, a benzene, a sulfonate, or a sulfite? All right, so right away here we see functional groups, right? And so you might have to remember back to your organic chemistry days to remember what these are. But remember, we're looking for something not on the protonated G acid. And so first, let's just go through these functional groups and make sure we understand what's going on. So an alcohol is an OH group attached to it, okay? That's probably the most common one you'll see over and over again, but an alcohol is very common. A benzene is a type of ring, and you'll see them in these hexagon shapes with sort of an aromatic structure. And so this is a benzene ring, very, very common, 6 carbons, and we will move on to sulfonate. Sulfonate, a little less commonly seen, but still, it's an S double bonded to an O, double bonded to an O with a negative charge, okay? And so that is what a sulfonate is. And so now we're on to our last one, and we're looking at sulfite. And what is that? That's an S with a double bond O, and there's an O minus and an O minus. So there's 2 negative charges on this functional group. So now with this information, we're going to go back to our G acid, right? And so right away we see we've circled an alcohol right here. So an alcohol is right there. And then we also see a benzene ring right here. I'll go ahead and put that in the color green. Oops. Color green. Okay. Benzene. And then what do we have here? Do we have a sulfite or do we have a sulfonate? A sulfonate. Well, we see that this matches our double bond, negative charge. Double bond, negative charge, right? And so with that, we can eliminate C. And if we look at the other one, it's identical to this double bond, O minus. And so it does not have a sulfite group, right? We saw the alcohol, we saw the benzene, we saw the sulfonate. We did not see that sulfite group. And so with that, we are 3 for 3, and we're on to the final question. And I really want to emphasize, memorize those functional groups, right? No one likes memorizing functional groups unless you love organic chemistry. But it's really, really helpful to get those free points on the MCAT, right? If you can identify those functional groups, that question wasn't too bad. But if you couldn't, very, very challenging. All right, now we're on to our final question. Researchers are likely to observe which of the following during a PNPP assay for EC 3.1.3.2 when pH is lowered to 5. A, cleavage of EC 3.1.3.2. B, an increase in inorganic phosphate levels. C, a decrease in sulfonate levels. Or D, a decrease in EC 3.1.3.2 activity. All right, so we're discussing what? PNPP assay, right, for EC 3.1.3.2. What paragraph did we discuss this assay and this enzyme? Well, we discussed it in these last 2 paragraphs, right? We see EC 3.1.3.2, the PNPP assay, right? And so right away, we should note that our notes are saying this assay works best at a lower pH and maintains an activity optimum at 5 and a higher pH, I think they said 8, yep, magnitude lower. So the question is specifically asking us, when the pH is lowered to 5, what's happening, right? And so if we're in that optimum range, right, that means the activity of that is going to be better, right? That PNPP assay is going to be working its best. It's going to show the most of this reaction occur. And so right away, we should say, okay, D is already out because it's a decrease in EC 3.1.3.2 activity. And we would expect the opposite of this. Okay, now let's go A through C, right? Cleavage of EC 3.1.3.2. Now, this is not mentioned anywhere, right? It does not say that the activity of the pH is increasing because of cleavage of the acid. It says it catalyzes the hydrolysis of monoesters, but it doesn't cleave the acid phosphatase itself. It hydrolyzes something else. So we can eliminate A immediately. B, an increase in inorganic phosphate levels. All right, so where does it talk about inorganic phosphate levels, okay? Here, it talks about inorganic phosphate right here in this reaction. So the acid phosphatase is taking this PNPP, cleaving it into PNP and PI. PI is this inorganic phosphate. So the way I think about it is, if we see an increase in this sort of acid phosphatase, that would mean we would have an increase sort of push to this side, right? We're pushing from left to right. If we start with a certain amount of a substance and that enzyme is functioning at a faster and faster rate, like it's performing at its optimum rate, you're going to have more of the products as opposed to the reactants, right? You're going to move from left and go to the right. And in this case, PI is expected to increase, whereas PNPP itself would be down. And so we can see B as our answer. And so C will look at a decrease in sulfonate levels. This is not mentioned anywhere in this last two paragraphs, right? We're discussing this PNPP assay. I do not see where it talks about sulfonate levels anywhere in this last two paragraphs. And so if we don't see any information to support an answer, we don't pick that answer. And we do B as our final answer, and we're 4 for 4. All right, great work, team. We crushed that Chem Phys passage. Kudos for you for getting it done. Lots of great stuff, from functional groups to equation work to acid-base definitions. So great job getting it done. Proud of you. If you like this video, give us a like down below and subscribe to our channel, and comment exactly what types of walkthroughs and videos you're looking forward to next. Additionally, check out our 528 strategy series from Vikram. Super helpful strategies that can help you maximize your studying before test day. And finally, click the link in our bio to sign up for the MCAT question of the day, so you don't miss out on any practice before test day. Happy studying, and let's get it.